Here's a question that sounds like it should have an easy answer. Which is bigger, the set of all whole numbers, 1, 2, 3, 4, going on forever, or the set of all even numbers, 2, 4, 6, 8, also going on forever?
The whole numbers, obviously. The whole numbers contain all the even numbers plus all the odd numbers. It is twice as big.
That is the intuitive answer. And it is wrong. They are exactly the same size.
Which is either a trick or the beginning of one of the most genuinely strange ideas in the history of mathematics.
Welcome to Philosophy for Lunch. I'm Shawn.
And I'm Claire. Today we are in the strange and certain pillar mathematics and the philosophy of mathematics. Specifically, we are talking about infinity, not as a vague gesture towards something very large, but as a precise mathematical object that turns out to behave in ways that violate every intuition you have. Ways that drove several of the mathematicians who worked on it to breakdown, obsession, and in at least one case, madness. Big ideas, human conversations. Let's go.
The first thing to understand about infinity is that it is not a number. That sounds simple, but it is the source of most of the confusion. We have a word for it, so we treat it like a number, something you can add to or subtract from or compare to other things. But infinity does not behave the way numbers behave. And the history of mathematics is, in part, the story of what happened when mathematicians tried to figure out what it actually is.
The ancient Greeks were deeply uncomfortable with infinity. Aristotle distinguished between two kinds: potential infinity and actual infinity. Potential infinity is the infinity of counting you can always add one more. The process never terminates, but at any given moment you have a finite collection. Actual infinity would be a completed infinite collection, not just the process of counting, but all the numbers, right now, as a finished whole. Aristotle accepted potential infinity as legitimate and rejected actual infinity as incoherent. He thought you could not have a completed infinite set, because completion implies a boundary, and infinity by definition has none.
That position held for a very long time. Medieval theologians complicated it by arguing that God was actually infinite, complete, perfect, unlimited, which introduced a theological dimension to the mathematical debate that took centuries to disentangle. And the mathematicians of the 17th and 18th century, working on calculus and the theory of infinite series, kept running into infinity without having a rigorous account of what they were dealing with. They were getting correct answers by treating infinity in ways that were not strictly justified, which made the foundations of calculus genuinely unstable.
The crisis came to a head in the 19th century. Mathematicians like Cauchy and Weierstrass worked to put calculus on a rigorous footing by reformulating it in terms of limits, getting rid of the informal use of infinitely small quantities and replacing them with careful definitions that only invoked finite numbers. That was a major achievement. But it left the question of actual infinity, what it means to talk about a completed infinite set, still unresolved.
And that is where Georg Cantor enters. In the 1870s and 1880s, Cantor produced a body of work that transformed the mathematical understanding of infinity. He did not just clarify it, he showed that infinity was far stranger and far richer than anyone had suspected. And the mathematical establishment, led by some of the most powerful figures in the field, reacted to his work with hostility that was, by the standards of academic discourse, remarkable.
One of his most prominent critics, Leopold Kronecker, called him a corrupter of youth and a renegade. Cantor spent years struggling for recognition, suffered multiple episodes of severe depression, and died in 1,918 inches a sanatorium. The story of what he found and what it cost him is one of the most dramatic in the history of ideas.
But before we get to Cantor, I want to say a bit more about why infinity was so troubling for so long, because it is not just a mathematical problem. It is a conceptual one that touches on logic, physics, and theology in ways that made people genuinely anxious about it for 2,000 years.
Zeno of Elea, a Greek philosopher from the 5th century BCE, constructed a series of paradoxes that exposed the problem with assuming space and time are infinitely divisible. The most famous is Achilles and the tortoise. Achilles gives the tortoise a head start in a race. By the time Achilles reaches where the tortoise started, the tortoise has moved a little further. By the time Achilles reaches that new position, the tortoise has moved again. The argument seems to show that Achilles can never catch the tortoise, because there are always infinitely many gaps to cross, each requiring some finite time. Yet clearly, in the real world, Achilles catches the tortoise immediately. Something is wrong with the reasoning.
What is wrong, we now know, is the assumption that an infinite series of positive quantities must have an infinite sum. It does not. The sum of 1/2 plus 1/4 plus 1/8 and so on converges to 1. The infinite series has a finite sum. Calculus, properly formulated, handles this without difficulty. But Zeno's paradox exposed something real. Our intuitive picture of infinity as simply very, very big was not adequate. And fixing the picture required 2,000 years of mathematical development.
Galileo in the 17th century noticed something that disturbed him sufficiently that he chose not to pursue it. He observed that you can pair every whole number with its square 1 with 1, 2 with 4, 3 with 9, 4 with 16, and the pairing never runs out. Every whole number has a square, and every perfect square has a square root that is a whole number, which seems to imply that there are as many perfect squares as there are whole numbers, even though the perfect squares are a proper subset. Galileo concluded that the concepts of more, less, and equal did not apply to infinite quantities. He walked away from the problem rather than follow it further. It took Cantor, 2 centuries later, to follow it all the way.
Let us go back to the opening question. Why are the whole numbers and the even numbers the same size, despite the even numbers appearing to be a proper subset of the whole numbers?
The key is how you define same size. For finite collections, two sets have the same size if they have the same number of elements. But for infinite collections, you cannot count them, you never reach the end. So Cantor proposed a different criterion. Two sets have the same size if you can put them in a one-to-one correspondence. If for every element in one set you can find exactly one matching element in the other, with nothing left over on either side, then they are the same size.
And you can do that with the whole numbers and the even numbers. Match 1 with 2, 2 with 4, 3 with 6, 4 with 8, and so on. Every whole number corresponds to exactly one even number, just double it. Every even number corresponds to exactly one whole number. Just have it. Nothing is left over. So, by Cantor's definition, they are the same size. Mathematicians say they have the same cardinality. The technical term for this size of infinity, the size of the whole numbers, is aleph null, the smallest infinite cardinal.
Which is already strange enough. But Cantor did not stop there. He asked whether all infinite sets are the same size, and the answer turned out to be no. Not all infinities are equal. Some are genuinely, provably larger than others.
This is where his diagonal argument comes in, and I want to try to convey it because it is one of the most elegant proofs in mathematics and does not require any technical background to follow in outline. The question Cantor asked was, is the set of all real numbers, all the numbers on the number line, including all the decimals, the same size as the set of whole numbers?
The intuitive answer might be, yes, both are infinite, so why not? But Cantor proved they are not. Suppose, he said, that you could list all the real numbers between 0 and 1, write them out as an infinite list, in any order. He then showed that no matter how you write that list, there is always a real number that is not on it, and he gave you a recipe for constructing it. Take the first decimal place of the first number on the list and change it. Take the second decimal place of the second number and change it. The third decimal place of the third number, and so on. The number you have constructed differs from every number on your list in at least one decimal place, so it is not on the list. But we said the list contained all real numbers. Contradiction. The assumption that you could list all real numbers is false.
Which means the real numbers cannot be put in one-to-one correspondence with the whole numbers. There are more real numbers than whole numbers. The infinity of the real numbers is strictly larger than the infinity of the whole numbers. Cantor called this larger infinity the cardinality of the continuum, and he showed it is equal to 2 raised to the power of aleph null, a bigger infinity, one of infinitely many larger infinities, as it turns out.
And this is what drove the controversy. Cantor had shown not just that infinity is a legitimate mathematical object, but that there is a whole hierarchy of infinities, an infinite tower of infinite sizes, each strictly larger than the one below. The landscape of mathematics was suddenly very different from what anyone had assumed. And for mathematicians who believed, as Kronecker did, that only the finite and the constructible were truly real in mathematics, this was not just wrong, it was offensive. A kind of mathematical mysticism, dressed up in formal notation.
Cantor himself was deeply affected by the criticism. He believed in his work with a conviction that had something almost religious about it. He wrote that he had been chosen to reveal these truths, that the transfinite numbers had been communicated to him from a higher source. Whether that was the language of genuine faith or the beginning of the psychological disintegration that eventually overtook him, it is hard to say, probably both. The mathematical establishment's rejection of work he knew to be correct, combined with what appear to have been episodes of bipolar disorder, wore him down over decades. He died in a sanatorium, largely unrecognized, having spent his final years writing letters to Francis Bacon scholars, arguing that Bacon wrote Shakespeare, the greatest mathematical mind of the 19th century, unraveling at the edges.
His work was eventually vindicated. Hilbert, one of the most important mathematicians of the early 20th century, called Cantor's theory of infinite sets the finest product of mathematical genius and one of the supreme achievements of purely intellectual human activity. The diagonal argument is now in every undergraduate mathematics curriculum. But that vindication came too late for Cantor himself.
Cantor did not just discover that there are different sizes of infinity. He left behind a question he could not answer, and it turned out to be one of the deepest questions in all of mathematics. The question is called the continuum hypothesis.
The setup is this. We have Aleph null, the size of the whole numbers, the smallest infinity. We have the cardinality of the continuum, the size of the real numbers, a larger infinity. Cantor's question was, is there an infinity that is strictly between these two, bigger than Aleph null but smaller than the continuum? Or does the continuum represent the very next size of infinity after Aleph null, with nothing in between?
Cantor believed the answer was no, that the continuum is the next infinity with nothing in between. That is the continuum hypothesis. He spent years trying to prove it and could not. He tried to disprove it and could not. It became an obsession. Hilbert listed it as the first of his famous list of 23 unsolved problems in 1900, the most important open questions in mathematics for the new century.
And the resolution, when it finally came, was not what anyone expected. In 1940, Kurt Gödel showed that the continuum hypothesis cannot be disproved from the standard axioms of set theory. In 1963, Paul Cohen showed that it cannot be proved from those axioms either. The continuum hypothesis is independent of the standard axioms of mathematics. You can build a perfectly consistent mathematical universe in which it is true, and a perfectly consistent mathematical universe in which it is false. Both are valid. Mathematics cannot decide between them.
Which connects to Gödel's incompleteness theorems, which are worth at least naming here because they represent one of the most profound discoveries in the philosophy of mathematics. In 1931, Gödel proved two theorems that shook the foundations of the discipline. The first says that any consistent formal system powerful enough to describe basic arithmetic contains true statements that cannot be proved within that system. There are mathematical truths that are beyond the reach of mathematical proof. The second says that such a system cannot prove its own consistency. Mathematics cannot verify its own foundations from within.
This was devastating to a program called Hilbert's program, the attempt, led by Hilbert himself, to place all of mathematics on a secure, complete, and provable foundation. To build a system from which all mathematical truths could in principle be derived, Gödel showed this was impossible. Not just technically difficult, in principle impossible. Every formal system of sufficient power either contains unprovable truths or it is inconsistent. You cannot have both completeness and consistency.
Gödel's proof is itself a remarkable piece of work. He constructed a mathematical statement that essentially says this statement cannot be proved, and then showed that if the system is consistent, the statement must be true but unprovable. It is a mathematical version of the liar's paradox, made rigorous, and it has been reverberating through mathematics and philosophy ever since, because it places a permanent limit on what formal reasoning can achieve.
There is something philosophically significant about the fact that the limits of mathematics were discovered from within mathematics. Gödel did not need philosophy or mysticism to show that there are truths beyond the reach of proof. He used mathematics itself. The ceiling was found by someone standing inside the room, looking up.
I want to say a bit more about what independence actually means in this context, because I think it is one of the most genuinely strange ideas in all of mathematics, and it tends to get glossed over. When we say the continuum hypothesis is independent of the standard axioms, we do not mean we have not yet found the proof. We mean something much more radical. Paul Cohen, in proving the independence result in 1963, constructed two different mathematical universes, two internally consistent models of set theory, in one of which the continuum hypothesis is true, and in the other of which it is false. Both are equally valid. Mathematics cannot adjudicate between them from the inside.
The technique Cohen developed to construct these models is called forcing, and it was a genuinely new tool in mathematics, a way of building models of set theory by carefully controlling what sets exist in them. It earned him the Fields Medal, the highest honor in mathematics. And what it showed is that the question Cantor had spent his career trying to answer was not, in fact, answerable from within the mathematical system he was working in. The continuum hypothesis is not true or false in some absolute sense that mathematics can access. It is true in some universes of mathematics and false in others. Whether there is a fact of the matter beyond that, whether one of those universes is the real one, is a philosophical question, not a mathematical one.
And that, I think, is genuinely vertiginous. We are used to the idea that there are mathematical questions we have not yet answered. We are much less comfortable with the idea that there are mathematical questions that have no answer, not because of any limitation of our cleverness or our tools, but because the question itself outstrips the capacity of the formal system to decide it. The floor of mathematics turns out to have trapdoors. I want to step back from the mathematics now and ask the question, this whole pillar is built around, what does any of this actually mean? Not just as a set of technical results, but philosophically. What does the mathematics of infinity tell us about the nature of reality, the nature of mathematics, and the limits of human understanding?
The first philosophical question is about the nature of mathematical objects. Are infinite sets real? Do they exist somewhere, independent of human minds and human mathematical practice? Or are they constructions, useful fictions that help us organize and extend our thinking about the finite world, but not genuinely real in the way a chair or a planet is real?
This is the debate between Platonism and various forms of anti-realism in the philosophy of mathematics. The Platonist and many working mathematicians are intuitive Platonists, even if they would not call themselves, that believes that mathematical objects are discovered, not invented. Cantor did not create the hierarchy of infinite cardinals. He found it. It was there, waiting. The diagonal argument does not construct a truth, it reveals one. And the truths of mathematics are, on this view, as objective and independent as the physical facts of the universe.
The anti-realist, and there are many varieties, from formalists who think mathematics is a game played with symbols according to rules, to intuitionists who think mathematical objects only exist when they can be concretely constructed, denies this. For the intuitionist in particular, Cantor's transfinite numbers are deeply suspect. Intuitionism was developed by the Dutch mathematician L.E.J. Brouwer, who argued that mathematics is a mental construction, that a mathematical object exists only if you can construct it in a finite number of steps. From this perspective, the actual infinite is not a legitimate mathematical object. You cannot construct it. You can only gesture toward it.
The intuitionist position has the advantage of being philosophically clean, no mysterious abstract realm of mathematical objects, but it comes at a significant cost. It requires rejecting large portions of classical mathematics, including much of Cantor's work. And most mathematicians are not willing to pay that price. The results are too beautiful, too coherent, too useful.
There is a third major position worth naming, which is formalism, the view associated most closely with Hilbert. The formalist says, the question of whether mathematical objects really exist is the wrong question. Mathematics is a formal game. We lay down axioms, we agree on rules of inference, and we derive theorems. The theorems are true in the sense that they follow from the axioms by the agreed rules. Whether the objects they describe exist in some metaphysically robust sense is outside the domain of mathematics, and outside the domain of what mathematicians need to worry about.
The problem with formalism, as Gödel's incompleteness theorems made vivid, is that it does not quite work on its own terms. Hilbert wanted to show that mathematics was complete, that every true mathematical statement could be proved and consistent, that it would never produce a contradiction. Gödel showed that no formal system powerful enough to do arithmetic can be both. Formalism, as Hilbert conceived it, was shown to be impossible as a foundational program. The game is richer and stranger than the rules can capture.
What most working mathematicians actually believe, I think, is a kind of pragmatic Platonism. They do not spend much time worrying about the metaphysics. They explore mathematical structures and report what they find, and the language they use discovering a theorem rather than inventing one, finding a proof rather than constructing one, reflects an implicit realism. The structures feel like they are there. The truths feel like they are true independently of anyone's mind. Whether that feeling corresponds to anything metaphysically real is a question they leave to the philosophers. And the philosophers, in turn, leave it mostly unresolved. The second philosophical question is about what the incompleteness theorems tell us about the relationship between truth and proof. Gödel showed that there are true mathematical statements that cannot be proved, which raises a startling question. If a statement is true but cannot be proved, what makes it true? If truth in mathematics is not the same as provability, then what is it? What is mathematical truth grounded in, if not in the activity of formal proof?
The mathematician and philosopher Roger Penrose has argued that the incompleteness theorems are evidence for a kind of mathematical Platonism that the human mind has access to mathematical truths that transcend formal systems, and that this is evidence that human consciousness is not itself a formal system. The brain is not a computer running an algorithm. It is something else, something that can somehow perceive truths that no algorithm can verify. This is a minority view among philosophers and mathematicians, but it is a serious one, and it connects the technical results of Gödel directly to deep questions about the nature of mind.
The third question is about what the mathematics of infinity tells us about physical reality. Does the universe actually contain infinities? In physics, when your equations produce an infinite result, a singularity, as in the center of a black hole, or in the initial moment of the Big Bang that is generally taken as a sign that your theory has broken down, the equations are pointing at something real, but the infinite answer is telling you that you have pushed the theory beyond its domain of validity. Physics abhors actual infinities in the same way nature abhors a vacuum. And yet, the mathematics of infinity is indispensable to physics calculus, which describes almost everything in the physical world, is built on the mathematics of the infinitely small and the infinitely large. The tool is everywhere. The thing itself is nowhere.
Which is one of the strangest features of mathematics as a human enterprise. It is extraordinarily effective at describing physical reality. Wigner's famous phrase is the unreasonable effectiveness of mathematics in the natural sciences. And yet the objects it invokes, infinite, sets, irrational numbers, imaginary numbers, geometric points with no extension have no obvious physical counterpart. We are using an abstract tool to describe a concrete world, and the tool keeps working even in places where the concepts seem to have no physical instantiation. Why? Nobody knows.
I want to spend some time on the human side of this story, because I think the psychological and biographical dimension is genuinely illuminating, not just as drama, but as evidence of something important about the relationship between human minds and the concept of infinity.
Cantor is the most dramatic case, but he is not alone. Bolzano, who did important early work on infinite sets in the early 19th century, worked in relative obscurity and saw his work suppressed by the Catholic Church. Frege, who tried to found all of arithmetic on logic and set theory, published a major 2-volume work and received a letter from Bertrand Russell the day the second volume went to press, pointing out a simple contradiction in his system that invalidated the whole project. Russell described Frege's response as one of the most admirable in the history of science. Frege acknowledged the contradiction in a postscript to the volume and conceded that the foundations of his work had been shaken. He then largely stopped working in foundational mathematics and spent his final years writing increasingly bitter and anti-Semitic political pamphlets. The collapse of his life's work broke something in him.
Russell himself, working with Alfred North Whitehead on the Principia Mathematica, an attempt to rebuild the foundations of mathematics that took account of the contradictions in set theory, spent 10 years on a project that filled 3 enormous volumes and was largely superseded by Gödel's Incompleteness, theorems within a decade of its completion. Russell later said the work had permanently damaged his capacity for sustained, abstract thought. He moved into philosophy and politics partly because the mathematics had cost him something he could not recover.
What is it about infinity that takes this kind of toll? I think there are a few things. One is the sheer cognitive demand. Working at the frontier of foundational mathematics requires holding in mind structures of enormous complexity and abstraction for years, without the external feedback loops that most intellectual work provides. You cannot check your intuitions against the physical world. You cannot run an experiment. You are navigating by reason alone, in the dark.
But I think there is something deeper. Infinity is one of the places where human intuition is most systematically wrong. We evolved to track finite quantities in a finite world. Our number sense, our spatial reasoning, our causal intuitions, all of these are calibrated for a world where things have sizes and edges and can be counted. Infinity violates all of that. And working deeply with it means spending years in a conceptual space where your intuitions cannot be trusted, where the results are systematically counterintuitive, where the danger of making a subtle error that invalidates years of work is constant.
Cantor's obsession with the continuum hypothesis is an example of this. He spent years trying to prove something he believed was true but could not prove, and it turned out that his failure was not a failure of intelligence or effort. The statement genuinely could not be proved. He was trying to climb a wall that, it turned out, had no top. The frustration of that, of working at the edge of the knowable and not being able to distinguish between "I have not found the proof yet" and "there is no proof," is a peculiarly modern form of intellectual anguish.
And Gödel's incompleteness theorems formalize that anguish. They tell us that in any system powerful enough to do interesting mathematics, there will always be truths that live beyond the reach of proof. The ceiling is permanent. The frontier is real and will not be eliminated by more effort or more cleverness. There are things that are true that we cannot know are true, by any means available to us within the system. That is not a temporary limitation. It is a structural feature of the mathematical universe.
There is something I find both humbling and oddly comforting in that. Humbling because it places a permanent limit on the aspirations of formal reasoning. There is no system of thought complete enough to capture all of truth. Comforting because it means the frontier never closes. There will always be mathematical territory that has not been explored, always questions that have not been resolved, always something beyond the reach of what we currently know how to do. The infinity of mathematical questions is, perhaps, its own kind of infinity, not the same as Cantor's transfinite cardinals, but equally inexhaustible, equally strange, equally beyond the capacity of any single mind or any single era to fully map. I want to say something about why I find this material so philosophically compelling, because it is a bit of a departure from the earlier episodes in the season. We have been mostly in psychology and ethics, the inner life, how to live, how to relate to other people. This episode is about mathematics, and yet I think it connects to the same set of questions.
The connecting thread for me is the encounter with genuine limits. In the Anna Freud episode, we were talking about the limits of self-knowledge, the parts of the mind that are structurally inaccessible. In the free will episode, we were talking about the limits of agency and the question of what we can ultimately be responsible for. In the grief episode, the limit was the sheer irreversibility of loss, the thing that no framework can fully resolve. And now we are talking about the limits of reason itself, the formal, provable limits that Gödel placed on what any system of thought can know about itself.
What strikes me is that in each case, the encounter with the limit is not just a negative discovery, it is also a clarification. Knowing that you cannot fully know yourself does not make self-knowledge pointless, it makes it more honest. Knowing that some mathematical truths are improvable does not make mathematics futile, it makes the landscape more accurately mapped. The limit tells you something true about the territory. And there is something valuable in knowing where the ceiling actually is, rather than spending your life assuming it is higher than it turns out to be.
Cantor's fate is a warning about what happens when a mind capable of genuine insight into the infinite is not matched by the institutional and personal support it needs to survive the discovery. The mathematics was right. The recognition came too late. And I think there is a lesson in that about how we treat people who are working at the edges of what is known, the difficulty of that work, the isolation of it, the way that being right about something genuinely counterintuitive can feel indistinguishable from being wrong for years, while the establishment lines up against you.
The last thing I want to say is about wonder. This is the pillar of the strange and certain, and I want to end by naming what I think is strange and what is certain here. What is certain is that the mathematics is correct, the diagonal argument, the incompleteness theorems, the independence of the continuum hypothesis. These are among the most rigorously established results in human knowledge. What is strange is that they are true at all, that the universe of mathematical structures contains infinite towers of infinities, each strictly larger than the last, that there are truths no proof can reach, that the tool human beings invented to count sheep and measure fields turns out to describe a landscape that is, in its own way, as inexhaustible as the physical universe.
Hilbert, near the end of his life, gave a radio address that ended with a sentence that has stayed with me since I first encountered it. He said, "We must know, we will know." It was his defiant rejection of ignorabimus, the Latin phrase for "we shall not know," the claim that some things are beyond human understanding. Gödel's theorems, published the same year, effectively proved Hilbert wrong about the completeness of mathematics. But I do not think the spirit was wrong. The drive to know, to push against the limits, to map the ceiling even when you cannot break through it, is itself one of the finest things human beings do. And infinity is one of the places where that drive has produced results of genuine, breathtaking strangeness.
I keep coming back to the image of Cantor in that sanatorium in his final years, writing letters about Shakespeare, the mathematics long since taken out of his hands by the breakdown. He never knew that within a generation his work would be foundational. He died not knowing whether he had been right or wrong, only that the people he most wanted to convince had spent decades telling him he was wrong. The vindication came after. That gap between the work and the recognition is one of the lonelier features of intellectual life at the edges. And it seems right to hold it in mind when we talk about what mathematics can accomplish and what it costs. Next week, we are back in History and Ethics, the Enlightenment, what it actually argued, and why the idea that reason alone can ground morality turned out to be more complicated than its champions hoped.
If this episode made the universe feel slightly larger and stranger than it did an hour ago, that is exactly what it was supposed to do. Share it with someone who is not afraid of that feeling.
Sources and further reading are in the show notes.
We are Philosophy for Lunch. New episodes every Sunday.
Big ideas, human conversations.
See you next week.